exactly.
We'll just give it a couple of minutes. Probably out looking for the pizza that we promised.
Sure, your show.
Anybody's calendar.
Really?
Because everybody's like, oh, you can just do this for free. Yeah.
That's funny.
Yeah.
So, hello. I would like to, can everybody hear me? Can you hear me down in Washington? Can you hear me down there? Thumbs up? Okay. So I'd like to welcome everyone to the 122nd Innovation Brown Bag. I'm John Griffith, and I'm very pleased to have the MIT Marine Autonomy Lab folks here today. We have Dr. Michael Benjamin, Dr. Misha Nowitzki, and Dr. Paul Robinette, and they're going to tell you about some of the work that they've been doing. So I've been sort of interacting with them for about 3 years. They do, well, one of the things that they do, I don't want to steal all their thunder, but they do capture the flag on the Charles River with kayaks and autonomous teammates. I've gotten to get in the water. A few other people have done that around here. We brought some summer interns to do that. It's a lot of fun. But they're actually doing science too. And so they're going to tell you a little bit more about that. And starting off is Mike Benjamin.
Great, thank you, John. Can everyone hear me okay? My name is Mike Benjamin. I'm with the Department of Mechanical Engineering at MIT, also the Computer Science and AI Lab. And John has asked us to come and give us a brief overview of what we do in the lab. There are several different projects we work on. The Aquaticus Capture the Flag human-machine teaming competition is one big one. But I'm going to try to put that in the context of some of the other things we do in our lab. So first off, this is always like to lead off with the folks who have supported us recently. These are our current list of sponsors, and you can see some of the usual characters there between a DARPA, ONR, but also industry sponsors as well. So we make it work from a lot of different angles. This is a little bit of an overview of the people that I work with. I work for both Professor Henrik Schmidt and John Leonard. They have 2 different labs on campus, the Marine Robotics Group and the Laboratory for Autonomous Marine Sensing Systems. Sort of if you took a Venn diagram of those 2 labs and you look at the Marine Autonomy Group, that's us. And there's Paul Robinette and Michael Nowitzki, who are with us here today. My former colleague as a postdoc, Paul Newman, who's now at Oxford, wrote the Moose middleware software that we use in our group, is also a colleague and a dear friend. And Professor Christos Dimitas hired me a long time ago from Sea Grant, and we have a relationship with Sea Grant as well. Actually, Paul is a member of Sea Grant. So some of our students, this is some of our lab space. We'll go into that a little bit more in a second. This is where we work out of, and this is where John has probably seen us most often. This is the Marine Autonomy Bay, we call it, a Marine Autonomy Lab. We are right here in this door that's open by next to that yellow kayak. It is the MIT Sailing Pavilion, so 99.9% of the stuff that goes on there is sailing. But a few years ago, they were nice enough to let us lease one of the garage bays there to turn it into a Marine Robot Lab. Hey, let it rip. A lot louder than I thought. I'm just going to temporarily turn that down, and there we go. Okay. So we just give an overview of some of the platforms we have. This is the bluefin sand shark. It's one of our smaller UUVs that we use for few different research projects on campus. It's a one see, and it's involved in a number of different projects for underwater sensing, underwater acoustic communication. I believe we saw one here today on the MITRE campus as well. Important part here is that we can launch this from the sailing pavilion. Our larger vehicles, the Bluefin 21, we still have 2 of these platforms, but you will rarely see these on campus. They're $1 million platforms that we've had for about 20 years with lots of different upgrades. They tend to live at Bluefin now, and we work on a few different projects there, and we prepare our vehicles and let them do that work. And we put in our autonomy and computing equipment inside and go to sea with them as partners typically. But there's an awful lot more you can do with this platform. But as you can see, you need a crane to get it in and out of the water. In the old days, 15, 20 years ago, this platform was actually deployed at MIT for testing, and it was a bit large for our testing purposes. We have these other smaller unmanned surface vehicles called Herons. These are made by ClearPath Robotics in Canada. These are our main teaching platforms for our students in our marine autonomy class. Again, they can be put into the water very simply with a single person. They're also platforms that we use for our ColRegs research. We also use them for our Aquaticus project as the robots in the human-robot teaming. A fairly larger vehicle, we have only one of these, is the WAM-V unmanned surface vehicle, as shown here. Dr. Robinette is going to talk more about that today and a couple projects that we have going on with that. We originally got this vehicle as part of the robotics competition back in 2014 when we took our students to Singapore for international robot competition, which we won. We got to keep the vehicle, and it's still a platform that we use for our research. And this is the vehicle in Singapore. So part of what we do also is we have periodic user group meetings. This slide is a picture of our 2017 users group meeting on the docks of the sailing pavilion, and some video footage of some of the groups that came. So I'm going to talk in a second about the open source software project we have for marine autonomy that we've had for about 12 years now. It's also evolved to the point where we have every other year a users group meeting, and the next one is this coming summer. This is some footage from this this past one. So people come, they come with their robots, they come with their ideas. Demo day now is part of this, so they can bring their platforms to the river and demonstrate what they're doing with the software in their vehicles. So this is our perspective on where the field is right now and where we might think it might be going, and gives you a little bit of an overview of what we're doing in our research. And the context is the role of open source software in all of this. So this is a video from back in 2006. It's kind of an important video for our lab because it was the first time that we ran our MIT marine autonomy software on any unmanned vehicle. In this case, it was a Bluefin 21-inch vehicle towing a large vector sensor array for a Navy project. It was very contentious at that time because the vehicle was expensive, the array was expensive, and the perception was that we were running this graduate student software for the autonomy system as opposed to the mature Bluefin software. I love the shot of the whale stuff. But anyways, the idea was that rather than running the vehicle software that came with the Bluefin vehicle, we instead were going to use the payload computer for this platform. And instead of just collecting science data on that computer, we're going to run our autonomy system and send heading speed depth commands to the vehicle and control the vehicle that way. It was a absolutely revolutionary concept at the time. Not that it was because it was so complex. It's actually a pretty simple concept, but no one was doing it. If you bought a vehicle, underwater marine vehicle back in 2005 or 2006, the only software you typically ran on that vehicle was the software that shipped with it, the vehicle manufacturer. So this was, for us, the first time that we ran our software as a guest or guest operating system on the vehicle. And it went very well. So After we came back from that trip in 2006, we launched the Moose IVP open source software project, and we started putting all this code online with the hopes of sharing with other groups, which is exactly what happened. So some number of years later, the software has been on at least these platforms. There have been many others since then as well too. But you can see sort of the variety of these platforms. They go from small research platforms to fairly large platforms on the surface, and underwater vehicles, surface vehicles, commercial platforms, DoD platforms. So it's a fairly flexible architecture. All right. It's another video I didn't kill. I thought I killed all the sound on these. Let me see. So where are we now? In 2014, in 2014, 2016, 2018, almost a decade, a little bit more than a decade later, this platform is used on a number of different types of platforms. Software is used on a number of different types of platforms. In 2016, which is an interesting perspective for us, that's 10 years after the Monterey Bay experiment. This one might need to be kickstarted. So this is the same bluefin 21-inch vehicle as in Monterey Bay.
I said that was impressive. It came into that maybe a foot or so.
And at this time, we're launching it under the ice in the Arctic. This is part of ICEX 2016, and we're be taking this vessel up to most likely up to ICEX 2020. We're on a trajectory to do that as well. The interesting thing here is that there needs to be a lot more trust in your autonomy system when it's operating under the ice. In 2006, if something went wrong with the vehicle, there were a number of different ways to throw a flag, pop up to the surface, and go grab your vehicle and start over again. But if you're operating under the ice, this video is sped up 10 times here. It's not possible or not advisable to just pop up to the surface, because you'll just be somewhere under the ice and it'll be very difficult to get your vehicle back. So where are we going in the next? Okay, so this is another sort of present day one. This is a project that we have with Textron Unmanned Systems down in Maryland. I'm not sure if any of you folks know about a vehicle called the Common Unmanned Surface Vehicle. It's a Textron name, but it's also a platform that's a program of record for the Navy as a mine countermeasures vessel. So they are working with us to integrate our autonomy software on their platform to do collision avoidance and obstacle avoidance. And we've been working with them since early this year with a few demos down in Dahlgren. So that's kind of where we are today in terms of the software. Barracuda is also another UUV that's a program of record for the Navy by Raytheon. And one of our recent graduates in 2015, Toby Schneider, integrated the MIT software onto this platform. So we've got a few different platforms that are DoD centric. There's a couple different companies, Aquaticus and Riptide, that ship their platforms with the Moose IVP software. Surface vehicles, there's Autonomous Marine Systems, which makes the autonomous sailboat on the left, and Sea Machines, two recent startups in the Boston area that have started with our software as their autonomy system. And this is another picture. I won't go into much detail because I think Paul probably has the same video. So this is a relationship we have with Mercury Marine to convert the Boston whaler into an autonomous vessel. So where are we going in the future? Our guess is just a guess, but it's worth talking about nonetheless, perhaps. So to understand where we're going, we might need to take a look back and see where we've been and why. And for me, that explanation starts with sort of looking at the component technologies that are on these platforms. So autonomy is just one piece, right? So there's the platforms themselves, and some of these trends are all of these trends are happening simultaneously and for the most part independently. The platforms are becoming cheaper and smaller and easier to deploy. The number of commercial platforms in the marine space over the last 10 or 15 years has exploded. So there's a lot of different options out there. It's no longer the case that just a few organizations with deep pockets have unmanned marine vehicles. When we first got those bluefin 21-inch vehicles back in the late 90s, there was a very select company that had these kinds of platforms that could afford the platforms to begin with, but also afford the ship time to deploy them. But now the platforms are smaller, they're cheaper, more people have them. You can deploy them from smaller ships, or you can deploy them from dockside. So the space of users and vehicles is growing very rapidly. The sensors have also become smaller and cheaper, and you can process more information now on board. Computing power as well. It used to be 10 or 15 years ago that our vehicles would go out, collect data, and we would analyze it after we retrieved our vehicle. Now the vehicles can collect data, process that data, and make conclusions about that data that the autonomy system can act upon while the vehicle is in the water. Launch and recovery has also gotten a lot easier. Acoustic communications, still a hard problem, and for the most part has limitations that are driven by physics. But we do know when we can communicate with each other, and for the most part, we can communicate with vehicles when the conditions are right and the software is very mature in that area. Another way of looking at it is that the autonomy missions that were around 20 years ago were very fixed, canned missions. You sent your vehicles out to certain points, you collected data, and then you sent them back out again. As the sensing and computing power has improved on these platforms, the vehicles no longer just collect data passively and return. They collect data and act on it, and which means you're changing your autonomy mission from something which is scripted to something which is non-deterministic and is acting on your data, which is wonderful, but it's a little scarier for users because they don't know exactly what the vehicle is doing at any one particular time because they may not know what it has just sensed. But it's great if you like AI or if you like autonomy because it means your missions are a lot more interesting now. They're no longer just scripted, but they can capitalize on their information. And as we have more and more vehicles and we're able to communicate between these vehicles, we no longer look at these vehicles as going out as independent operators. They can work in collaboration with each other, and that changes the complexity of your autonomy mission as well. So where are we going in the future? So this is a video. I'm not sure how many of you have seen this. I just took a clip of this. This is Rolls-Royce's vision for the future, autonomous shipping. And the interesting thing about this video is the role of the human. So there's a command center, which is quite elaborate for a concept video. But nevertheless, the idea here is that there's a remote ship which is constantly connected to a human with a lot of different ways of visualizing what's going on and keeping track of what's going on with the platform. So the hidden message here is that the ship doesn't necessarily need to be 100% all the time fully autonomous from dock to dock. That is, there's a lot of monitoring going on that sometimes involves humans. And if you can involve the human in the right way, you don't have to necessarily solve that last 1/10 of 1% of the autonomy problem. That you can deploy these vessels and bridge that gap with human connectivity. So we think, and that's the reason why Dr. Nowitzki and Dr. Robinette are brought into our group, is that HRI, or human-robot interaction, human-robot teaming, is a big part of the future for marine robots and robotics in general. So we think HRI is going to be one of these other component technologies of all unmanned marine systems in the next 10 years. And so that's another way of looking at it. So I will talk a little bit about autonomy education. I know that's not necessarily the focus of our meeting here today, but it's a lot of what I do and what we do, so I'll talk about it for a second. Let's see. So starts with the recognition that robot software is an ecosystem. So a lot of times when we hire students or undergraduates to work in our group and they want to do autonomy, they want to write behaviors, they want to get right to the AI, which is great. But one of the not so secret secrets is that there's an awful lot of software that's running on your vehicle and in the lab in order to be able to concentrate on the autonomy software. So there's simulation, mission planning software, sensor drivers, post-mission analysis software. All these things require many work years of effort to develop that make up in the end an ecosystem of software that we use, which of writing actual autonomy code is only one small part. But our objective is to create this ecosystem where you can jump into it and write autonomy code much more quickly. And another way of looking at that too is, software has its own set of layers, or you start. This is almost a description of our development of software over the last 15 years. It started with a robot middleware called Moose, and we built our autonomy architecture on top of it, which included behaviors and math libraries, and then all the utilities that I just mentioned that make this important to work with. And if we want to share this with other people, as students, and work with it in the classroom, we also need to develop documentation. which is just tells you how the software works, but also training material, which means example missions and labs in order to be able to use this. And so there's an awful lot of work that's invested in this. It's gone back at least 15 or 20 years now. So we teach this class called MIT 2680, Marine Autonomy, Sensing, and Communications. It's taught in the spring semester, and it's very hands-on. Students will spend time with robots. In the last 6 weeks, they will spend most of their time on the water deploying robots in a number of different missions that we give them as challenge problems. Another perspective, I won't go into this, but big picture is back in 2000, the people who were working with autonomy on marine vehicles were a couple of faculty on campus. Henrik Schmidt, John Leonard, and Jim Bellingham. Shortly after that, we had postdocs like myself and Paul Newman that came along and started working with this, but it was still a very select company. And in order to be able to make this more available to students and eventually bring it into the classroom, we developed software that we very tightly controlled in terms of version control and documentation. And over time, we have been able to introduce this to the point where people are getting their PhDs with this software, using the software, which is a 4 or 5 year period of time they're on campus. And then eventually master's students were able to use this software to work with their master's thesis all the way to 2018, where we are now, where we teach it and use it in undergraduate class. So our goal is to expose more and more students and make the level of the bar of entry smaller for people to get involved in this field. And this is our classes for the last few years. So they're not huge classes, but it's very hands-on and very tight-knit. So I'll talk a little bit about robot architectures, software, what's inside of a robot system. If any of you were to take a guess from end to end, if you had to write all the software from scratch, what would your guess be in terms of the number of years it would take to write that software? Anyone want to venture a guess? 25? All right. Any others? 200? That's great. So my guess was right in between. It was like 50, right? So we're, it all depends whether you're writing the C++ compiler or, you're starting with it, So, and that's my, my first point is we are leveraging an awful lot of things that are in the open source environment, and we fully acknowledge a lot of those tools that make this even remotely possible to think about. But on top of that, we have robot middleware, and in this case, we're using Moose as our middleware. Paul Newman wrote Moose, and it was probably his third time of writing a middleware. Even if you just look at the lines of code that are in Moose, you have to count the number of lines of code and all those generations before that actually got you to that point. But the component software, and then on top of that is an autonomy layer. And so there's a number of years of investment there as well. And I say zero work years at top because if you have a lot of this software, if you take this software that's in the public domain, you can literally bring a robotic platform to market within a year. And this is evidenced by Riptide in the upper right-hand corner, C Machines in the bottom left, and Raytheon, who developed the Barracuda vehicle using this software and did not have to reinvent all of that stuff in the green. So that's kind of where we're at. This is where we live. The Moose IVP Autonomy Project is probably the common thread for our lab. It's what I do most of the time in my day job, but it's also used in these other projects that we're talking about as well. The common thread of this is our payload architecture principle. We call this the payload autonomy architecture. In this case, the key idea here is that your autonomy system is running in a payload computer on the main on the robot talking to the main vehicle computer. And so what this means is that you can decouple your autonomy system from your platform. You don't have to live with the software that Bluefin sells you with their vehicle or Hydroid sells you with their vehicle. You can use that, but you don't have to. It's very liberating. And so again, we're sort of living at the software at the tactical world, and not really so much the software at the control level, which we tend to use at the main vehicle computer for on the platforms for that software. We use, in our case, in our classroom, we use this thing called a PavLab, which is just short for Payload Autonomy Box. It's a Raspberry in a box, and actually, I was in Henrik's office yesterday, and I think he gave me one of these that he had been borrowing, so I just happen to have one of these in my backpack. If anyone wants to look at it, it's not very impressive. I've seen things a million times more impressive on your benches here. But this is what we use as our payload autonomy system. We hand out those boxes to the students, and they each have one for the semester. They download the open source code onto that. They get the software ready, prepare it onto their vehicle, and they drop it into the robot, as you see there, and run their labs. And what this means is that the student is no longer tied to a particular platform either. So they can just come and find whatever vehicle is running well that day and has charged batteries and just go into that platform. And so this is just a time-lapse video of us making a bunch of Pablos. So the second architecture principle is that inside that autonomy system, we have an open source software project called Moose, and it's a publish and subscribe architecture. It's a very lightweight middleware. It's about 10,000 lines of code and has no software dependencies and runs under Mac, Linux, and Windows. We prefer it ourselves compared to ROS and LCM, which are other alternatives, which have their own strengths and drawbacks. We can talk about that afterwards too if you want. One of the applications is the Helm, and that's our autonomy system, and that's the third architecture. It's a behavior-based architecture that does multi-objective optimization for behavior reconciliation. So all of these things, the three things here, they give end users flexibility. So we don't have to buy our autonomy system from the same place we buy our vehicle. That's a huge freedom right there. And our autonomy system is made up of publish and subscribe modules. So we don't have to get all of our autonomy software from the same place either. We can bid on these things or create a meritocracy of components there as long as they publish and subscribe the same thing. So that's very liberating for the user as well. And then inside the actual autonomy system itself, which is the thing that's actually making heading speed depth changes, that's an architecture which is behavior-based, and you can augment and add things to yourself as an end user. So this makes things a little bit more complex if you just want to buy a system that works. But if you want to develop a lab that's developing new capabilities and being nimble and providing your users with new capabilities, this architecture gives you an enormous amount of freedom. And that's what we've found too. So Moose IVP is an open source architecture. Moose is a middleware. IVP is the Helm architecture, those two architectures I just showed you. They're both open source and they're both online, and they both support commercial proprietary software add-ons as well. So the architecture itself is a GPL license. The libraries that you need to link to write new behaviors into Moose apps are LGPL licenses, so that means you can write proprietary components on top of it if you want. Quick overview of the Helm. The Helm is just another Moose app. At the beginning, for steps 1 and 5, it reads mail and it publishes mail. But in between, it triggers a number of behaviors which can influence the control of the vehicle. When those behaviors are competing for control of the vehicle, it does a form of multi-objective optimization. That's what IVP is. And then ultimately, it comes with the decision and publishes it back to the autonomy system. This is happening 4 times a second, typically. And so this is a little animation on the right of 2 behaviors, one doing collision avoidance on the upper right, and one with an objective function that steers you towards a waypoint. And so behavior is basically taking sensor values or human commands. They also take in initial configuration parameters, and they produce objective functions and ultimately things that can be posted back to Moose. So a waypoint behavior takes in the waypoints. It takes in sensor values, so it knows where you are as you're steering towards those waypoints. It might take in human commands that tell you to change directions or come home. But ultimately, that behavior will produce an objective function and Moose postings. And Moose postings for waypoint behavior, an example might be something might be published every time you hit a waypoint. So we had one user that wanted to go from waypoint to waypoint, have their vehicle stop and change into a station keeping mode to drop a sensor, collect sensor information, have another flag published when that sensor was retrieved, and go off to the next waypoint. So the beauty of this system is not necessarily the multi-objective optimization. That is an important part, but the interesting thing that our users have found over the years is that you can stitch together novel missions by using the building blocks of the behaviors without having to write new code. So this is another way of looking at the same thing. This is our runtime input, which is where we are in the field, navigation, X and Y. You take as your list of waypoints, and the objective function that's being produced by the Helm is shown in the upper right. And if you were doing collision avoidance and obstacle avoidance at the same time, you would see both a collision avoidance objective function on the bottom right and the transiting objective function in the upper right. And this is what the collective objective function might look like if you add those two together. And in our case, these behaviors, as they're producing these objective functions, they run it through a solver. The solver does a form of multi-objective optimization. which takes the weighted combinations of those original objective functions and comes up with a heading and speed command or a depth command too if it's an underwater vehicle. So the takeaway of all of this is that as a developer, you can develop behaviors relatively independently of all the other behaviors in a system. So there's a lot of things that are behavior-based about this, and there's a lot of things that are not in terms of traditional definitions of behavior-based control. But one of the key things that we adhere to is this notion that you can incrementally augment your autonomy system with new behaviors. And users can do that partly because they have access to the open source code, partly because the interface in terms of the output of these behaviors is an objective function in a very common format and a solver that will handle all the combinations. So it's easy to augment your autonomy system. So this is what that same thing looks like as an animation. I don't think, oh, that one's not going to play. So we'll move on. So the secret sauce for us is that these objective functions are piecewise linearly defined. And the reason why that's important is that we don't care what the underlying objective function is. As a behavior author, your design of your behavior ultimately must be able to rank possible heading and speed or depth commands for a candidate maneuver. And that objective function may be nonlinear, may be non-convex, may be discontinuous, may be bimodal. There's all kinds of different ways that objective function can look like if you're a behavior author. And we don't want to put constraints on behavior authors that you have to give us a unimodal objective function, for example. So behaviors ultimately produce a piecewise linear approximation of whatever's under the hood for that particular behavior. And the reason why that's great is that now we're just dealing with pieces. We don't really care what the underlying objective function is. And so these are some examples of objective functions that look like for other behaviors: a collision avoidance behavior, a stand-on behavior. And the ones on the right are actually the same objective functions, but it just shows that you can use large pieces to represent huge plateaus in some of these objective functions for efficiency. And we use a form of branch and bound search to be able to do multi-objective optimization on this. So I'm going to touch in the last 5 minutes here on some projects, and then I'm going to turn it over to Paul and Misha. Which one of you guys is going next? Misha? Okay. So one of our projects that we work on is a project called the call regs. And I don't think this video is actually going to play on this one, but this was, it's a fun video, it's too bad. But this is the Port of Amsterdam on a holiday. There's a lot of traffic that's moving along. And collision avoidance is a big problem, even in the open ocean. There are still regularly, almost every other week, you hear about a major collision happening between ships. And if we ever want to have autonomous ships or autonomous surface vehicles in the open ocean, collision avoidance is a huge part of the hurdle to get trusted to do that. So we have developed this project called the call regs project, which is essentially development of one key behavior in our autonomy system, the call regs behavior. And so the goal of this project is to look at the most common scenarios in collision avoidance, which are the head-on situations, crossing situations, and overtaking situations, and develop behaviors that allow us to do collision avoidance. So we do this based on reasoning about closest point of approach, which is just a very simple mathematical calculation, especially if you're looking back retrospectively to see what the CPA was. But if you want to calculate a CPA from a known location and starting position and calculate that CPA looking forward, it's a fairly complex calculation. But we use CPA and we apply that to a particular ownership and contact situation. Then we apply a metric to it, which is our tolerance for collisions and our tolerance for safety. And we go from this objective function on the left to the one on the right. This is purely a CPA-based objective function. And we can use the tricks in our software to find plateaus in these areas here and develop objective functions with smaller numbers of pieces. And we had a paper on this recently. You can look at it if you want to. So this is the how that objective function evolves as vehicles maneuver. So this is collision avoidance without call regs. This is just using that CPA objective function I showed you, and it can be pretty dicey. Again, this is a deceivingly hard problem, even though it's a very simple pattern, because the vehicles are steering towards the same waypoint, and they're also you're also telling them not to collide with each other. So you notice there are some non-call regs maneuvers, and that was definitely a non-call regs maneuver. You're supposed to turn to the right in a head-on situation. But again, these vehicles are just thinking about closest point of approach. They don't know anything about protocol. And you can get inefficiencies as well, too. We've all done that in a little bit in the hallway, right? You just sort of do that dance a little bit. Vehicles would do that, too, if you didn't have protocol. So, so the reason why that happens is the CPA objective function here, as it's approaching a contact, has no bias to either side. And if the other vehicle is doing the same, they both may non-deterministically turn in the same direction. So we tried to capture the call regs rule by adding a bias into our objective function. And if both vehicles have the same right turn bias, we get a lot better results. We do the same for crossing situations and overtaking situations. This is the same simulation with the call regs protocol added, and it's a lot less interesting. Vehicles just tend to do the right thing in the right circumstances. So we do a lot of our testing on the water and its simulation. Our simulation testing involves generating scenarios where we think we can get a lot of crossing, overtaking, and head-on situations, and running software as we move along to test for collisions or near collisions. So we can collect this data. One of the tricks, as I mentioned before, the dirty secret of writing robot code is that there's also a lot of other software that needs to be written. So we've invested a lot of time not only in developing the call regs behavior, but in the software that can go through that mess on the right and be able to find interesting things. So we're able to, in this case, the simulation that has 1,000 encounters, we're able to find a couple interesting results. In this case, in an earlier version of our call regs, we had 2 near collisions or collisions. We're able to plot this entire simulation with this tool that generates what we call encounter plots. And we can find the anomalies here and the 2 anomalies shown, and then go back and replay that data and then analyze what went wrong and then fix our software. So that's call regs. The project that Misha will talk about is Aquaticus. That's a human-robot teaming project based on Capture the Flag. We played this on the Charles River on the field that we shown there. The idea is that each team is comprised of 2 humans and 2 robots, and they have to work together. So as a human, you need to be able to understand your autonomy system and adapt your autonomy system while the game is unfolding. I'm not going to talk a lot about this because I think that's Misha's primary talk. This was a video we took in our first year of, it just gives you an idea of the platforms. So the humans are in these motorized platforms, and our robots, which are platforms on the dock you see there. Misha, do you have this video in yours? No. Oh, okay, nonetheless. And the other project that I think Paul is going to talk about is something called the Boston Harbor Robo Challenge. And that involves our unmanned surface vehicle, the WAM-V that we call Rex. And Rex is involved in a couple other different projects, not just this project. Let's see. So the challenge there is to be able to launch our vehicle from the Charles River and get it out into Boston Harbor through the path we show there on the right. But there's an awful lot of challenges there in terms. There's locks, drawbridges, and lots of things that require a robot to deal with humans as the vehicle is moving through that space. Let's see. Oh, I am not going to play that. I swore I turned down all these videos right beforehand. But this was a video we took before we started the project, really, just to show what this journey looks like from the motorboat's perspective. So we just went through an old lock there. Here we're going underneath a drawbridge, which we were able to sneak under because we were short enough, but our robot won't be able to. And this was just some pictures of in-water testing recently. And so that's essentially it. The last thread that often gets overlooked is that we have this program during the summer. We call it the Summer Marine Robotics Internship Program. It really serves Aquaticus mainly. But there's students there that have this last year worked on the larger vehicle, the Rex vehicle. And it's a way to engage students at the high school level and undergraduate level early who are interested in this kind of field. And it's worked out really wonderfully. Misha runs that primarily, and in terms of recruiting students and running the day-to-day operations, it's been very impactful for us. That's it. I'll leave it there. So. We're going to wait to questions afterwards, right? Okay. I will leave you. Do you want my power? Do you want the mic? Okay. I'll shut this off here. Get out of your way.
Mike, could I have the dongle, please?
Yes.
Thank you. All right, hi everyone. I'm Michael Novitsky. I go by my Russian nickname Misha. I'm here to present to you the project Aquaticus, which we've been doing at MIT since I got here as a postdoc in 2015. What is Aquaticus? So it's human-machine teaming, playing capture the flag on the Charles River. As Mike has already showed you, we have a lab here at the MIT Sailing Pavilion. We leverage a whole lot of their resources like their motorboats and local relationships. Our playing field goes roughly along the edge of the dock here and coming out maybe a quarter of way into the river itself. If you don't remember capture the flag, it is two teams. Typically, one team has a flag at their home zone, and your goal is to go grab their flag and bring it home, and that's how you score points. The way you defend your flag is by tagging people on your side of the field. When someone is tagged, they have to go back home to untag themselves. And in this case, we made it really exciting because humans are in their own vehicle while they have robot teammates. So this is another view from this year. You can see that the side closest to us is the red team. The side furthest away from us is the blue team. In a full game, it gets pretty hectic. We can have up to 8 vehicles on the field at one time. So like I said, we have a lot of resources at our disposal. So we have safety boats out there and different people watching for safety. So what are we trying to look for in Project Aquaticus besides having a lot of fun? We're looking at the intersection of human-robot trust, operator cognitive load, and robot autonomy. We find that playing with these different knobs, we're trying to see exactly what can we come with out of it. So because of time, I'll just go ahead and show you some of the current, the top one is the Army MUM-T program that's actually happening, and then you'll hear the Army refer to MUM-T on a regular basis, even at the West Point. There in the current example, they have an Apache helicopter where the co-pilot can manipulate one of the drones that they have at their availability and go around and look at waypoints or what have you. The other project that's pretty similar is the little Air Force Wingman project, where they're trying to have fighter pilots talk to actual F-15s that are autonomous. I have no idea the state of that project. They're kind of quiet. So our robot teammates, of course, we don't have access to fighter pilots or fighter jets, but we have access to the water, and we have marine robots that we buy from ClearPath. We heavily change them and modify them for our own purposes. Typically, we do a lot more with these robots than other groups do, including a big red button, just in case someone needs to push a big red button while doing some of their, didn't do it. Mm-hmm. So I could keep talking, but then you guys can't see what I see.
Yeah, they are.
So it says it's seeing the screen. No.
No, we're just broadcasting the video offsite. There we go. Wait.
Awesome. Thank you.
Thank
All
you,
right.
Tom.
So the ClearPath Heron robot, the M300, we add, like Mike already explained, we have a PavLab box in the back for autonomy, and Paul's been helping with getting power supply to that. We've ruggedized it over the several years to make sure it works for us. The robot autonomy, so right now we're writing a bunch of papers, and it's really hard for us to explain to people exactly what we mean by robots. For us, our robots are fully autonomous. And that means I can just give them a command, and they just go and do it, right? So there's no remote controls. The only people that have remote controls are for safety, and they're back on the dock, right? So when the available behaviors that we can give these robots, I can ask the robot to attack, which means they'll go from our home side to the opponent side, grab the flag and come back, all while avoiding collisions, which is courtesy of Mike's collision avoidance protocols. And other available things are defend, cover, follow, station. The defend is pretty simple. Cover and follow are team coordinated things. So if I have the flag, I can ask my robot to cover me or follow me, and that way we can maneuver together and they can block tags. The human vehicle is fantastic. It is a Mokai, which can be bought for about $5,000. It already comes with a joystick and a gas engine in the back. We, of course, modify it so that we can use it as a node on our network, compasses, GPS, and of course, a local computer so we can plug in a headset. We had to go with ruggedized headsets because, of course, we're in the water and we have the engine in the back and it's super loud. So we have one that people use for racing. Here you can see some of the other instrumentation that we've added inside. So when you sit in the cockpit, this is exactly your view. That way you can see we have radios and other things going together. We also try to put sensors on the human. We are hoping to look at cognitive load and try to see how that can get changed based on different things we do. We're in the early stages of that, but I do have an example here. If you're looking at the upper right of the chart, you can see that our participants' heart rate kind of goes down, they're chilling, and then there's a spike in the middle. Someone had actually encroached on the field and was coming in their way, and they got kind of nervous and didn't know what to do. So their heart rate spiked. And I thought that was really neat just to see that. I enjoyed that a lot. You can also see that we had a camera facing the person. Here's an example of what the person experiences when they're looking out. It can get pretty wet, so we have a windshield, but still sometimes that's not enough. This also looks like kind of a rough day. You can see the waves creating a little bit of turbulence. It really is a lot of fun if you guys ever have a chance to come. I know that you've been bringing interns in yourself for a while. We try to use everything over our local network. That way we can record everything as is happening and have timestamps, because then when you're doing data analysis later, it makes it much easier. Our interns are fantastic, like Mike has already said. We had some over the summer put together using open source Mumble software, which is people use it for gaming and talking back and forth. It allowed us to use that to talk with each other. And here we have how we talk to our robot teammates. So our robot teammates require a little bit more work. So we have a very simple dialogue manager that is waiting for a command. I say to my robot, blue one attack. And the robot will then ask me, did you mean that? Because speech recognition isn't the best. And you want to kind of avoid sending errant messages back and forth. And you can acknowledge or decline that command. In fact, I think if audio works, I have an example that I just put together over Thanksgiving.
Blue 3 defend.
Did you mean blue 3 defend?
Yes.
Command sent.
So that's a little taste of what it's like to talk to your robot.
Blue 3 defend.
Teammate. All right, so what we've noticed is a lot of different things. So we've only had about 2 actual 4-on-4 games that we're able to keep. A lot of things happen to data. People constantly, the river is not exclusively ours, so people are constantly coming in there. Hardware, of course, is not always reliable, even though we spend a lot of time on it. But we have been able to do some observational data, and what I've seen for sure so far is that people are very different, and we're just grabbing random people to be teammates, and personality differences tend to kind of show up on the team. So we're going to need a whole lot more participants and a whole lot more teams to try to figure out exactly how things go. But here you see an example of a team that actually spent some good amount of time talking to each other. So on the top, you see game events. So that's when the game says to you, someone has a flag, someone's been tagged. Below that, you see I'm transmitting over VoIP. Below that, receiving over VoIP. Below that, you see the transmission and receiving from talking to the robot. So this person in blue 2 was very vocal talking to their human teammate, which is great. So they talk about different things. If they're having problems with speech recognition, they have the other person take care of that for them. They talk about strategies. Here, the person only talked to the robot at the beginning and then at the middle of the game to give them commands. Now, red 2 and the red team was a completely different story. So red 2 was constantly talking to his robot, you can see that at the bottom, and talked to his teammate, like twice at all the whole 10 minutes. We have no idea what started that. But it's a really fascinating just to see that kind of comes out of, even though we didn't make that a initial thing to look at. So let's listen to what it's like for a person. So we try to make it as realistic as possible by having everything coming over through the audio commands. However, it's very confusing. So I want to let you guys experience what it's like to be listening while you're actually playing the game. So this is a participant. This is what they experienced while they were actually playing. If I can get it to.
Sure, if you click that, just try clicking on the arrow again.
Blue 1 has the red flag. Red 1 has the blue flag has been returned. Red 3 has the blue flag.
So you can see that if there's a lot of things happening on the field, it can get quickly overwhelming. So when there's a serial events happening, you kind of follow, but there's so much excitement that you kind of lose track of what's happening. So what we've been asked to do is start implementing multimodal interaction with our human teammates. And so we've been prototyping different LED bars so that we can give the person in the cockpit some information about what's going on. So No Man's an Island, I have to have like a whole lot of people help with this project. One experiment takes about 15 of our own researchers, plus other support staff in the different boats. So we rely heavily on some really fantastic high school and undergraduate students. All this work has been approved by our human use to be publicly available. So any of this stuff, if you already want to come look at the website, you can certainly download any of the data that we have and you can look at it. And it includes a video of the person in the kayak, the audio of what they're hearing, the audio of what they're saying, and of course their location, and then their robot teammates' internal autonomy thought process. We have several different data sets. So like I said, the full game is 4v4, and we have 2 of those. One 3v3 was just opportunistic. One of the human vessels wasn't working, so we're like, why don't we just send a person out with 2 robots? That should be fun. And we just throw them out there. Then we have some 2v2 games, which were much easier to run, where you have 1 human and 1 robot playing as 1 human, 1 robot. And what we quickly identified was that there are a lot of confounding effects that happen with being outside and having multiple people on teams. So we decided to try to get a little bit more scientific, and that's how we came up with our half-court game. So with the half-court games, that allows us to focus a little bit on just scenario-based events and trying to manipulate things. So I'll get into that a little bit later. So here is an example of a splash page. So if you are interested in this data, you can go and look at it. It has an example videos to see exactly what transpired during the game, so you can preview it, and then how many players and their views, if that's available. So here is a sped up view of what a game looks like. The colors are things happening, like they're trying to tag someone. If you get tagged, you become a green color. If you get the flag, you carry the flag with you. So I mean, it's just chaos. It's fun chaos. Yes. So this is, if it's available, the drone footage is also included in there. It is not always guaranteed to have drone footage of our games. It depends a lot on our resources. But here's a view of, you can see, and it starts getting sped up, of the vehicles playing. From this view, it's very hard to see which team is what, but it also gives you another context for what's going on. Qualitative results. So we already found out that humans are pretty confused about the game state just because everything's happening over audio. We're taking steps to take care of that. We have different levels of people. When I say levels, of experience in working with teams. So if we grab a student off of the campus and then shove them in there, they have, maybe gaming experience. When we bring in other more experienced people, like an Army Ranger, they have different feedback for us from the system. What we're hearing a lot from those kind of operators is that they don't want to have to acknowledge what the robot's doing, or they don't really even want the robot to have to be told what to do. They want the robot just to go, and then they can check on it and then give us a different command. So that's fascinating all by itself. We currently have a lot of training time to get this used to it. Speech recognition hasn't been our best. It's about 80% accuracy using the Julius open source speech recognition engine. We're looking at using Google, which gets us up to 95% accuracy, which is great. So some of the experiments that we've been doing and publishing on include doing half-court experiments where we have a robot playing defense and only one human going to capture the flag. What we were interested in here was, would you trust a robot to be your teammate based on how capable they are in performing their job? So here we have two different modes for the robot. A simple mode is it simply orbits the flag and will just tag you, and it has no idea where you are and just waits there. It's opportunistic. The more advanced or aggressive behavior actually hunts you down as soon as you cross the line and will intercept you, tag you, and then chase you off the field. So it is a very good way to describe it, as aggressive. So we wanted to see which robot would you prefer to have. And it's pretty clear that a lot of the participants wanted the aggressive robot to be their teammate. And it said, we weren't trust that. So yeah, you could say this is a very obvious find, but without getting some numbers, we didn't really know. And now we can keep moving forward and trying different things. We have a bunch of papers. We're putting more in to publish. One of the difficult things that we saw on the tour, we talked a little bit with some of the virtual reality people here at MITRE, was that during the winter, we're off the water because it gets way too cold. The human use people won't let us be on the water because the participants are freezing, and it's kind of miserable for us as well. So what we're hoping to do is start putting in some proposals for actually creating a 3D reconstruction of this with not augmented reality, but virtual reality, so that people can play the games indoors so we can keep getting experiments and working data. We're also working with the United States Military Academy at West Point to do experiments as a capstone project with them. I can't really talk about that until they actually get that to go. Thank you for paying attention. I really appreciate it.
I know we're coming up on the end of time here, but I'll give you a couple slides about our project with the Boston Harbor Robo Challenge, and then we can talk more after if anybody's been interested in more details. Okay, cool. Let's go back to the beginning. All right, so I'm Paul Robinette, and I'm going to talk a little bit about the Boston Harbor Robo Challenge. This is a project that involves myself, Misha, Mike, and our grad student, Greg. Just briefly, Mike touched on a lot of different places where autonomous shipping is going to be in the very near future. And for autonomous shipping to be in the near future, it's one thing to have a boat go all the way across the ocean by itself, where there's not all that much stuff that you could potentially run into, and not too much trouble you could get into that you can't solve with like a satellite radio or something. It's another thing to ask them to go down canals and rivers and busy harbors like we have in the Boston area. So our specific problem is to take Rex, which is the vehicle up in the top right there, and have it navigate from the sailing pavilion out to the harbor. Our motivating example for this is that half of my funding comes from MIT Sea Grant. That's very much interested in ocean science, ocean health. One of our big projects there is to go out and with the robot, do some depth profiles with our SON to measure pH and alkalinity and other sorts of variables for ocean acidification out in the harbor in 11 different points. The robot goes out there, it goes to a waypoint, it drops a winch, it picks it back up, does it very consistently, more consistently than if you just sent a high schooler out on a motorboat, which is how this is traditionally done, and comes back. The trouble is we used to have to manually drive it with a remote control to get out there, then put it in autonomy, but take over whenever there's a ship coming through the harbor, then put it back in autonomy and back and forth and back and forth. So instead, let's have our boat, it's a robot, go autonomously from the sailing pavilion all the way out to the harbor and out to the bay beyond that on its own. And of course, regulations being what they are, we're probably not going to be sending it out without a chase boat anytime soon, but that means fewer people need to be on the chase boat, and we could be testing more interesting things at the same time. Specific challenges here, the Charles River, especially our area, is one of the busiest, if not the busiest, recreational waterways in the country. So you can get very busy times like this, which was some parade happening a few years ago. But every day we have people out in sailboats, paddle boards, kayaks, everything else in the middle of the river. And they all want to go see what the cool robot is in the middle of the water. We have narrow sections of the river. We have a railroad bridge that Mike was talking about that's on the middle right there that we have to call up over VHF radio and ask them to raise and lower it for us. And then we have locks that we have to signal with the horn and then wait for traffic lights to get through another narrow area where there could potentially be lots of traffic, and lots of interesting dynamics as the water raises and lowers inside the locks and the robot has to station keep. But then out in the harbor, we have more traffic. So just a couple of examples here. These are real examples taken just opportunistically over the summer. The paddle boarder just going right next to the robot on the water. Robot has LiDAR on it, but they didn't know it wasn't actually turned on at this point, right? We're testing something else. So they don't know what the robot's doing, but they show up anyways. And of course, every sailboat on the water needs to do a lap around the robot no matter what, no matter whether we're in the harbor or out on the river, anywhere. Some of our recent highlights here is that we've been working a lot last year and this year on data collection. So data collection, so we can spend the winter time writing software and algorithms to actually move along this area using LiDAR data, radar data, etc. This year, we've towards the end of the season, with Misha's help, we got some actual LiDAR integration with our obstacle avoidance system so that we can do some obstacle avoidance autonomously on the robot. And working on tighter integration with our chase boat, Philos, which I'll have pictures of in a minute, but the Boston whaler that Mercury has loaned to us. As well as some coal regs testing. So Mike has done a lot of great coal regs work. Rex is going to need that work when it hits the harbor and to get out to the harbor. So we have some cool videos on that in this. And then, of course, like I said, data collection for the off season. So just briefly, anybody who's worked with LiDAR, this probably looks pretty familiar. But we have our Velodyne HDL32. We're sending it to a Moose app that has PCL built into it right now, and then sending it to an off-the-shelf obstacle manager that comes with Moose. It's called P-Obstacle Manager if anybody else is interested in using the same sort of thing. We basically give it the point that it wants to avoid, and the helm will autonomously avoid it for us. So once we give it the sensor data, it works great. This is just a little from a log replay where we had some testing. We had our motorboat out there as the target to be avoided. We had it station keeping in one spot and had Rex come up. You can see the little circle of dots there is where it detects the center of mass of the motorboat, and the robot successfully avoids it and then proceeds back to its waypoint. So just one little demo of what we're doing. We have a couple of technical reasons we need to improve upon this to get more than just a handful of obstacles in the area, but that's our winter project for now. Like I was saying, we need to be able to do coal regs on the water, especially with bigger vessels. We go through the harbor and we get things like the LNG tankers coming through, highly explosive. The Coast Guard gets very nervous when you have robot boats in the water at the same time. And then any other sort of commercial shipping, tour boats, ferry boats, all sorts of traffic out there. So we tested this one by having the robot follow the whaler there. And that was autonomous following. The whaler's broadcasting its location. The robot's broadcasting its location so it can follow it that way. And then had a Mokai come in and just cross the path in the middle so that the robot would have to react. And in this case, the Mokai is also sharing its position over Wi-Fi, but because we have LiDAR integration now, we could potentially do that separately, just completely integrate without the Mokai on the same channel. So this was the view from the back of the motorboat as we're driving along, and then Misha and the Mokai comes and is told to drive straight at the robot, and it avoids him. Interesting thing to note here is that I believe the robot's actually supposed to be the stand-on here. So the robot's moving along, following the whaler and thinking, there's a target coming at me, but by coregs, it's supposed to move out of my way. And then, of course, it doesn't, so the robot has to take evasive action at the last minute. Yeah. And this is, you'd think that everybody follows the rules of the road on the water, but they really don't. If you go out to the harbor, yeah, the people doing whatever they feel like doing. And then this was the Mokai view of that. So you can see us on the whaler there. And this was from the same run, so you can see driving straight at the robot, and at the last second, it turns out of the way and avoids. We've been doing a lot of sensor evaluation. This is partially for the Harbor Challenge project, and partially we have a new project with Mercury Marine and their parent company, Brunswick Corporation, to work on a sort of operator assist for motorboats, because a lot of people buy these big motorboats, and it'd be great if we had better control systems for them to use as they're using and feel more comfortable as they drive the motorboats. So Mercury was kind enough to send us a radar, a stereo camera, and a thermal camera to mess around with. So we've been doing that for the last couple of weeks. We got these in September, October. So we quickly integrated them with the system so they're all time synced and then recorded data. And that's our winter project then to take this type of thermal data from the FLIR and make some sense out of it. You can see buoys a little bit better in this than you can potentially see them with LiDAR and anything else because they tend to get lost in the water. You can see boats really well because the engines light up nicely. And you can usually see people pretty well. So our goal with this is to be able to just sense the environment better, but also detect swimmers in the water, anything else that the boat might need to know to stop or avoid. The stereo camera, I don't know if anyone's played with a Z camera, but their stated range is something like 20 meters. For a indoor robot, that's great. For a robot on the water, 20 meters is basically nothing. So if you're 20 meters away, you should have already stopped by then. But you can see the depth image on the right here as we're going through the old locks. We can see some of the walls, so this could be used for near-in or docking situations. And then coming up, we have just been integrating some of our radar view. So this is a top-down view of the robot by the sailing pavilion up towards the top there. The orange is the LiDAR data and what the LiDAR sees, and the blue is what the radar sees. So the LiDAR sees a really narrow 100-meter range around us. The radar can see up to something like 8 nautical miles. We had it here set to 250 meters, if I remember right. And so we can see much further, but obviously the lower resolution. So what we're working on right now, we took this data at a lot of different ranges. This is, from here you can see the bridge going across the Charles River in the opposite bank and just about any obstacle along the way. We took this at a number of different ranges. We're trying to figure out what's the optimal middle ground where we have good enough resolution but also good enough range to supplement the LiDAR. So just to wrap everything up, we've been making progress towards our goal of getting to the harbor by developing new subsystems for obstacle avoidance, for COREGs, and for navigation, integrating new sensors and analyzing data from these sensors to determine what the final sensor suite is going to look like. And then over the winter, we're going to be working on finishing the integration and deploying this in the spring, ready to go. Yeah, and logical follow-on work from this, like Mike was saying, you can solve 99.9% of robot autonomy problems, but there's always that 0.1% that's going to get you. So some reliable remote operation, especially as we get out to the harbor and face unknown situations. The ability for the vehicle to request that remote operation will also be necessary. And then interoperating with the harbor traffic and the authorities on the river. And that's someplace we've been looking into recently, talking to the Coast Guard and the state police about what they want to see out of autonomous robots as they get out to the harbor. So that's all I've got for here. Thanks for your time. And I don't know if we're going to questions now.
What do you think? Bring on line as well. Does anyone here have any questions?
You have companies leveraging the platform. Are they contributing back to the platform?
Answer is, I guess, yes. In this case, the most recent that Paul had up on the screen with Mercury, they have contributed back in terms of support and in this case equipment that they've loaned us. And some of the companies that are using the software, it's not so much that they're contributing back in terms of sending us software, but they do send us a lot of very valuable feedback on how the software is doing and what they'd like to see out of it, which is very valuable to us. And in some cases, they make that software available to other groups, not necessarily in the public domain, but they make it known that it's available.
I have a question. I was interested that there's so many collisions with ships. With humans, how do you see the autonomous vehicles faring better, worse, the same?
It's a great question. I don't know. And it's not a black and white question of whether it's going to be human-based ships and autonomous ships. There's something in between, which is augmented capabilities for manned ships, decision aids, and things like that. There are strengths and weaknesses, and this has parallels to the autonomous car community as well. Robots don't get distracted. They don't fall asleep. They can do closest point of approach calculations for large numbers of ships, very, very quickly. But humans are also better at looking at common sense as well, trying to infer intentions of other ships, trying to balance their collision avoidance with other mission objectives. We feel that some form of multi-objective optimization is what's going on inside of humans' heads, and also needs to happen on the robots as well. But being able to gather all that information and work with it reliably is still a challenge.
So it's
Well, yeah. Ultimately, if you're going to have a ship operating autonomously, then it's an either-or situation. But we are looking at how this software could be, or these algorithms could be used as decision aids as well. And there are certain cases where even some of the news reports that we've seen of the Navy collisions, especially around the Strait of Singapore and other high contact density areas, is that it's a very, very challenging problem for humans in certain high contact density situations to look at all those ships and their various trajectories simultaneously and come up with a good solution. And if a little bit of that sensor information is wrong, one ship is going faster than is expected, or it's just not online, it can be very, very difficult for humans to make decisions.
Are you looking into any sort of systems where different platforms can share their intent with respect to where they're planning to move?
Yes, one of our students, Navy student, Lieutenant Joe Levitt, did his master's thesis on sharing intent and what its effects are on Colreg's collision avoidance. So it is something that we're looking at, or at least that student was looking at. We don't have an active project funded to look at that any further, but in certain cases, we do think it can be helpful. It's not clear that it can be helpful in all cases, just because there's that issue of whether intent is communicated properly and acknowledged properly. But in certain situations, it does seem obvious that it could be useful. For example, one of the hardest problems in Colregs is dealing with the vehicle during a stand-on mode. It's the easiest mode to implement, just keep your heading and speed, but it's also the most restrictive. And so most of the time you're in a stand-on situation is when a vehicle is crossing behind you or overtaking you. And if you can get intent from the vehicle that's doing the crossing or overtaking that it's intending to cross behind, it may free up the stand-on vehicle to be out of stand-on mode earlier, which can be very beneficial to avoid collisions if there's another vessel in play.
Online or in Washington? All right. Okay. Well, thank you very much. That was great. I also wanted to belatedly welcome and thank our partners at Draper and JPL and Lincoln Labs who've been watching as well over YouTube. And I actually, so we have, if you guys want to come up, we have a little memento for you to remember this event by. So, Paul, here's a certificate for you. Misha, one for you. And
Thank you.
Michael, one
Thank
for
you
you.
very much. Yeah.
Thank you very much.
Number 122.
Number 122.
Operating with some FFRDC.
What? No. M18.
Oh, but the L is listed on there.
No, they are.
I know they operated.
Yeah, maybe they are connected to them. I don't know. But there's some methodologies that follow the YouTube video. Would you like to go?
Yeah.
To continue discussing with the people who gave the talk? We go to a different room.
Oh, no, okay.
What?
Sorry, can you
We go to another room on the 4th floor.